Good morning, everybody. Your brother's back on the channel. Today I'm gonna work on ESP32 best home automation system design. So keep watching. So this is my indexing for ESP32 home automation system project. Here you can see in serial number 1 we have system block diagram that comes in sheet number 2, and serial number 2 power tree diagram comes in sheet number 3, so and so forth. Okay, and down here I put some text in there like sheet number. Currently it is 0, 0, 0, 1, and revision is 0, 0. And down here I put my name, I mean your nursery brother's name, Jakangara Nursery. Okay, that you want to follow in your system design. I mean, in the first and foremost you want to put your sheet number 1 for indexing. Okay, and right up that I put system block diagram, I mean in the sheet number 2, like you have seen in your indexing. Okay, let me go over this block diagram once before we jump to the next sheet. Okay, as you can see in this block diagram, I have ESP32 module in the middle. This is just an 32-bit RIX processor. It's a dual core processor. It is suitable for my project. Okay, and I thought to design my system with ESP32 SIF from scratch, but I would need 4 layers of PCB layer stack off. That would add production cost. So in order to minimize my production cost, I choose this ESP32 tiny module. Okay, and this module operates on 3.3 volt. So as you can see, I mean at the left top corner we have this power supply unit that consists of an SMPS that outputs 5 volt at 4 ampere, but I estimated it to be only 1 ampere in my system. But I thought that my system should be, I mean it will be reliable. I mean if I had to add extra loads in future, so I'm keeping this to be at 4 ampere, I mean 20 watts. Okay, and in here I have small, I mean tiny little voltage regulator, which is an LDO that converts this 5 volt power rails to 3.3 volt, and that goes all the way to ESP32 module and some sensors and other components on our system. And then down here I have temperature sensors and LDRs, but I'm not including LDR in my system, sorry for that. Temperature sensor is required in this system because our systems, I mean my system's gonna operate in two modes, either uh, you know either to be controlled with an Android phone, or to be operating in autonomous mode. And then down here I have tried AC dimmer. This is not suitable for inductive load. If I had to control the speed of the induction motor, this is not a suitable one because it generates humming sound. So I kept this trike AC dimmer for only resistive load. If I had to dimming the AC resistive load like light bulb. Okay, and then down here I have some GPIOs for interfacing general purpose input and output. And up here I am putting this AC dimmer release. It means if I had to control the speed of inductive loads, like speed of the AC ceiling fans, since I can control the speed of the AC ceiling fans with trike AC dimmer in a proper way, because it generates humming sounds, which is kind of annoying. So I'm planning to do that, and I came to an idea. If I could control the speed of the ceiling fan, like we have typical AC ceiling fan speed controller with bunch of capacitor. So that's how I come up with this idea of controlling the combinations of AC capacitor and some sort of relays in order to control the speed of AC ceiling fans. That's we're gonna you know see in the actual schematic. And up here I have three general purpose relays, and then here I have SPI display header for interfacing TFT graphical display for displaying some graphics and then text. And on the top of it we have USB to UART, and again on the top of it we have USB connector, as you can see here. This is for programming and debugging purposes. Okay, right after that I have power tree diagram that's gonna tell you which one of those components on your system consume what voltage level. Like as you can see here, this pipe ball is output produced from this SMPS in conjunction with this 220 volt AC at 50 Hertz here in India. Again, as you can see, this 5 volt power rail goes to 3.3 volt voltage regulator, which is an LDO, and then relays, USB connector, and zero crossing detection circuit. This is the part of AC strike dimmer circuit. Again, this voltage regulators outputs this voltage 3.3 volt from this power rail 5 volt, and that power rail goes to ESP32 sensors and some headers, and then this CP2102 and SIP, which is a which is an USB to which is a USB to UART converter. Okay, so this is it about this power tree diagram. This is very important. Okay, you want to include this power tree diagram as well in your system design. And then okay, this is the power supply unit that includes an SMPS socket that outputs 5 volt and an LDO that regulates 5 volt to 3.3 volt. The SMPS circuit is designed with a tiny little VWM signal controller IC, which is, okay, let me zoom it in, TNY280VN, that has a switching MOSFET already built in it. Okay, at the input section of this circuit you notice this an EMI or AC input filter circuit existing. And here I have EE25 ferrite core flyback transformer. This topology is kind of kind of looks intimidating, but it's really simple if you try to understand this circuit. The topology of this circuit is taken from the typical application diagram already given in data sheet of this particular IC that I'm using in this circuit design. If you still cannot understand this circuit, please let me know in the comment box. So now let me move to the next schematic sheet, which is USB to UART converter schematic. So this is my USB to UART converter schematic sheet, and I'm using this CP2102 for conversion of this USB to UART. Okay, and here I'm putting this USB connector for the communications to be happen between computer host and then this device during the programming and debugging. Down here you can see this 3 ESD protection diodes connected on this differential phase signals of 90 ohm, and also on this power line. And here we have a reverse protection diode. The reverse standoff voltage of these 3 diodes is 5.5. Okay, let me zoom it in. It means any voltage larger than that, the reverse breakdown regions of these 3 diodes starts conduct. Okay, and then down here we have this control circuitry designed completely based on this truth table. Notice this. This is just these are the NPN transistors. This is just a combination of these NPN transistors based on this. And I'm also including this external programming header for programming and debugging purposes through UART communication. And then now let's move to the next schematic sheet, which is MCU. In this MCU section I'm using okay, let me zoom it in. This obviously this ESP32 tiny module. Okay, Along with that, in this circuit section, I have these two switches for reset and boot switch, and SPI display interface, and then temperature sensors. And these are the general purpose IOs, which are used for the controlling the bunch of relays. You can see this net name. I mean, any nets with the same net names are interconnected with each other. You can see during the PCB layout design. Okay, and then we have three position SPDD switch for selecting the modes of this. I mean, the mode of operations of this system, either in autonomous system or in, I mean, to be control with an Android phone over Wi-Fi or Bluetooth. And here I have zero crossing and AC dimming. These two pins, AC dim and zero cross, is for tri AC dimmer circuit. We have also two SPI. Sorry, I'm so sorry. Yeah, we have SPI interface for display interface. You can see MOSI, MISO, SDK, so and so forth. What I want to mention here is serial I2C communications, which is connected simply to the which are connected simply to the test point in my system, because I'm not including any I2C communication. Okay, so this is it about this MCU. This is the brain of my system. Let's move over to the relay driver circuit. Okay, so here's my relay driver circuit. The circuit is an EMI compliance and design in such a way that any signals coming up the MCU are separated from these noisy signals. As you can see, this optic copper right here is separating these signals coming up the MCU from these noisy signals. And I'm also connecting this pre-wheel die pretty close to this relay in order to dampen, I mean prevent from electromagnetic interference produced during turning on and off of this relay. Okay, and also at the output of this relay, you can notice this snapper circuit in parallel to this MOB. This is very important if the output of the relay has to be connected with the inductive loads. Besides that, you can also notice this bunch of AC capacitor connected in a series with the output of those relays. They're acting like resistors in order to limit the amount of current flowing through it, thereby controlling the speed of inductive motors like AC ceiling fans. The reactance of those AC capacitors is Xc equal to 1 by 2 phi Fc. It means the larger the value of the capacitor, the larger the amount of current can flow through it. And then the smaller the value of the capacitor allows the smaller the amount of current flowing through it. Okay, and in parallel to those AC capacitor, you see this bleeder resistors connected in parallel in order to drain the charge store down onto the capacitors. So this is it about this relay driver circuit for controlling the inductive loads. I mean the speed of the inductive loads. And in the next relay driver circuit, I'm simply putting this in a general purpose relay driver circuit. This is pretty simple with only those snapper circuit with in parallel to MOBs for the protection of the circuit from inductive loads. And in the next schematic sheet, I'm putting this AC dimmer circuit. So please have a look at this. So now let me move over to the actual PCB layout design. So now I'm gonna open up PCB editor. So I double click on this. Okay, it's gonna open up in a while. Okay, so here's my PCB layout design that I kind of worked on yesterday. It is yet to be completed. As you can see, I have successfully placed all of these critical components within this specific form factor in such a way that the components on the sensitive signals are separated from the components on the noisy signals. And in this area, you can see this power supply circuit. And in this power supply circuit layout design, you can see this yellow mark that indicates the board cutout that isolates the DC signals from the AC signals, and the transformer over here separates the primary side from the secondary side. Okay, so now I'm gonna continue on designing this layout, so keep watching.